del 2u over del t square minus c naught square del 2u over del x square equals to 0. Okay. And this can also be written as if we are assuming that u is a smooth function, then can we write this PD in this form? See, when you will operate this operator on this, then what you will get? Del 2u over del t del x plus c naught oh sorry. So if u is a smooth function of x and t, is a smooth function of x and t, then del 2u over del t del x is equals to del 2u over del x del t. This is the property of a smooth function. So this term will cancel out, and this is our given PD. Okay. So this PD can be written in this form, and we can see that the solution of this will be the solution of this. The solution of this means we are getting the value of u which is satisfying this equation, and ultimately it will also satisfy this equation. So the solution of this PD will be the solution of this PD. So this is the simplest PD. We are going to discuss the solution of the PD. Okay, so the methodology we are going to use to discuss the solution of PD, solution of this PD, is known as the method of characteristics. Is known as the method of characteristics. So write a differential equation dx t over dt equals to c naught. Write a differential equation dx over dt equals to c naught. So if u, that is a known function, is function of two independent variable x and t, what will be the total derivative of u with respect to t? What will be the total derivative of u with respect to t? It will be the partial derivative of u with respect to t dt over dt, that is basically 1, plus the partial derivative of u with respect to x and dx over dt. So this is the chain rule. The total derivative of an unknown function u, which depends on the independent variable x and t, will be the partial derivative of u with respect to t and the partial derivative of u with respect to x, and then dx over dt. And if we are taking dx over dt equals to c naught, if we are taking dx over dt equals to c naught, so what it will be? And that is equals to 0. That is equals to 0. It means as soon as we are taking the ordinary differential equation dx upon dt equals to c naught, then the total derivative of u with respect to t becomes 0. It means along this curve, u is constant. Along this curve, u is constant. So these curves are known as characteristic curves. These curves are known as characteristic curves. And what was our initial condition? What was our initial condition? Our initial condition was u x comma 0, u not x. So when you solve this x becomes equals to c naught t plus suppose a constant xi, where xi is an arbitrary constant, where xi is an arbitrary constant. And if u equals to constant, if u equals to constant, then what will be the value of u? Can anyone tell me what will be the value of u? It should also satisfy the initial condition, is not it? So this u should be equals to u naught xi. This u should be equals to u naught xi, because since u is constant and it will also pass through this initial condition, so its value should be equals to u naught xi. And if we put the value of xi from here, then it becomes u naught x minus c naught t. Basically xi equals to x minus c naught t. So let's have a look at the profile, how I am explaining this physical phenomena. At t equals to 0, x equals to xi. At t equals to 0, this is your axis, this is your x-axis and this is your time axis. So at t equals to 0, this is your 0, 0 coordinate. So at t equals to 0, x equals to xi, that is a constant and that's vary over all the real line. And x equals to c naught t plus xi is this curve. Okay, it means this u, it means the information of u goes along this curve, because u is constant, only x and t change. If you fix x, then only t change. So this u is constant along this curve, that is a straight line in this. It means along this characteristic line, u is a constant. So in a simple form, we can write along the curve given by dx upon dt equals to c naught, the PDE. This PDE, suppose it is equation number 1, becomes an ODE given by du over dt equals to 0, and its solution is u equals to constant, that is u naught xi. This is called the method of characteristic. Okay, now you can ask me how you can say that this is the unique solution of the given PD. So let's cross verify. What I said, that this is the unique solution of the PD, which I derived with the help of the method of characteristic. So to verify it, we will differentiate with it with respect to t and x, and we'll keep it in this equation. If it satisfies, then this is the unique solution of that PD and also satisfy this initial condition. So let's verify. U equals to u naught x minus c naught t. So what will be the derivative of u with respect to x? The derivative of u naught with respect to augmented function, that is u naught dash, and then the derivative of this augmented function. So the derivative of this augmented function with respect to x, what becomes? 1 minus 0, that is del u over del x is u naught dash. Similarly, when you calculate del u over del t, so the derivative of this u naught with respect to the augmented function, that is u naught dash, and then the derivative of this augmented function with respect to t, that is 0 minus c naught. So basically it becomes minus c naught u naught dash. And when you multiply this term with c naught and add in this, so what it becomes? That is equals to 0. It means it is satisfying the given system of partial differential equation. So it is a solution of partial differential equation. Now, if it also satisfies the initial condition, then we will say that it is a unique solution of the given partial differential equation. So let's see whether it is satisfies the initial condition or not. So at t equals to 0, this is ux comma t. At t equals to 0, ux comma 0 becomes u naught x. It means it is also satisfying the initial condition. And that proves that the solution which I have derived with the help of the method of characteristic is a unique solution of, this is a unique solution of given PDE. Okay, so I told you that the solution of this PD is wave equation because it was the solution of a wave equation del 2u over del t square minus c naught square del 2u over del f. I will also tell you that it also represents the flow of, suppose you take some pollutants, suppose you take some colors and just drop it into a stream which flow from left to right. You drop some color at some point, then what will happen, that color will start to propagate with the direction of the stream. That is, that color will start to propagate from left to right. So that kind of phenomena with a constant speed, suppose that speed is c naught, then that kind of phenomena is represented by del u over del t plus c naught del u over del x equals to 0. So suppose if u is the concentration of that colors or pollutant, u is the concentration of a colors or pollutant which we spilled in a stream with a constant speed c naught, then the evolution of u is given by this partial differential equation, a very simple first order partial differential equation. And this partial differential equation is also known as advection equation. Basically, it gives you the evolution of that pollutant with respect to time and also space, which flow from left to right with the speed c naught. Why I mentioned you that it is flowing from left to right? The reason behind this is only that c naught will be positive when it moves from left to right. So for the moment, we will see the beauty of the method of characteristic. Okay, so the method of characteristic is applicable in linear PDE, in semi-linear PDE, and in also quasi-linear PDE. So it is applicable in the three forms of the PDE: semi-linear, linear, and quasi-linear, but not in fully non-linear. Okay. What we see that this solution with the initial condition u x comma 0 equals to u naught x propagate with a constant speed, and u is also constant along the characteristic x minus x equals to c naught t plus xi. So we will see its geometrical representation, what is happening. At x equals to 0, t equals to 0, xi will be 0. So that characteristic will emanate from here. Suppose xi equals to 1 by 2, so it goes here. Xi equals to 1, so it goes here. Xi equals to 2, so it goes here. So basically, this is the characteristic. This is the line t equals to 0. This is t coordinate. This is x. T equals to 0 here, and also x equals to 0 here. What is happening? In this characteristic, our u is constant. Our u is constant. So after a finite time or after a time t naught, so This is at t equals to 0. After a time t equals to t naught, whether the form of u will change? Does the form of u will change? No, it is constant. It will flow in this characteristic. It will goes along this characteristic. What will happen? So the solution at any, suppose it is u naught x, it is basically your initial condition, and after some time the form of u will be changed, only it displays with time, it will not displace in u. So the solution at any time t can be obtained first by displacing each point on the profile with distance c naught t from left to right. So basically what it is saying, the solution at any time t can be obtained first by displacing each point on the profile with a distance c naught t. Only distance will change. Means our curve will be some, if this line is at t equals to t naught, so it will go here. It will go here. Only the points, the pollutant is displacing with the distance c naught t. There is no change in the form of u naught, only the pollutant is displacing with the distance c naught t. It is going here from here to here. So basically what is happening, if I am seeing u only, suppose this is u, what is happening? At some time t equals to 0, it is here, and at some time t equals to t naught, the shape of the solution will be same. The shape of the solution will be same because it is the same initial condition. Only it will displace, it is at t equals to 0, and then it will displace at time c naught t. So this is at t equals to t naught. So what kind of observation we are getting? What kind of observation we are getting? We can see that the form of the solution doesn't change. It only displays with time with a distance c naught t. It only displays with the time with the distance c naught t, but the form of the solution doesn't change. And what happens in the wave phenomena? What happens if you see the sine wave or cos wave? What happens? The form of the wave is same. So basically what we are seeing, that the form profile is same. It means it is a kind of wave phenomena. That is, the solution of an advection equation is a wave phenomenon. The same signal will be recorded after a time t naught, where each point is moved to right with distance c naught t. Why we are saying that this is moving towards right? Because this c naught was positive. That pollutant in the stream was flowing from left to right. So that's why each point is moving towards right. That is from left to right, because this c naught is positive. That is, since it is representing a wave phenomena, it is transmitting an information from one medium to another medium without changing the form of the information. It is transmitting information from one medium to another medium without changing the form of the information. A signal is going from one medium to another medium without changing its strength, without changing its form. Okay. So what we did? We find out the solution of this partial differential equation with the initial condition u naught x. The intention behind this method of characteristic was to tell you about the hyperbolic partial differential equation. This is a hyperbolic partial differential equation of Cauchy problem. Why I am saying it is Cauchy problem? A first order partial differential equation with a smooth initial condition, a first order partial differential equation with a smooth initial condition is known as a Cauchy problem. A first order partial differential equation with a initial condition. What I told you, this EU is a smooth function of x at time t equals to 0 with a smooth initial condition is known as Cauchy problem. So we derived the solution of a hyperbolic Cauchy partial differential equation. Why it is hyperbolic? Because it is well posed. A partial differential equation is called hyperbolic partial differential equation if it is well posed. A partial differential equation is called a hyperbolic partial differential equation if it is well posed. So let's see what is the definition of well posed. Let's see what is the definition of well posed. If the solution of a Cauchy problem exists, if solution exists, it is unique and it depends continuously on the initial datum. It depends continuously on the initial datum. So what happened in this PD? We could see that the solution of this PD exists. It was unique and it also satisfied the initial condition. So this Cauchy problem was well posed. It means this Cauchy problem, is it hyperbolic or not? Is it hyperbolic? Yeah, it is hyperbolic because its solution exists, it is unique, and the solution depends on the initial data. Means the problem is well posed. It means the given PD is a hyperbolic PD. So this moment we talk about a very simple first order PD. Next, I think how much time I have left? I think I have left with only 10 minutes. Yeah, I have left with only 10 minutes. Okay. Next, I am going to discuss the solution of a typical first order hyperbolic PD. A typical first order hyperbolic PD, that is a Cauchy linear or semi-linear, that is basically different from linear. With the initial condition u, x, y is also function of x. This is basically t equals to 0. You can write here t or some y is function of x equals to u naught x. Okay, अगर आपको इसके पहले कोई डाउट है then please ask to me. किसी को please ask to me if you have any doubts. Yeah, please ask to me. Someone has raised their hand, so I think they are trying to ask something. If you guys have any doubt, then please ask to me. Another, I will proceed with this Cauchy linear partial differential equation. Okay. I am proceeding with this Cauchy linear partial differential equation. Here we can see that. Oh, don't worry. I will share this slide to you. Means I will share this slide to Professor Rahul, and then he will distribute this slide to all of you. And I will also share the PPT of the today lecture so that everything will be clear to you. Don't worry about the notes. Don't write anything on your paper. Don't write. Just try to understand. So here we can see that's the coefficient of this first order partial derivative is function of x, y and u as well. It means it comes in the class of Cauchy linear partial differential equation. Okay. So we want to find out the solution of this problem satisfying the initial datum u x comma yx equals to u naught x. So what will be the solution? The solution will be form of this. The solution will be the form of u equals to u x comma y. Rahul sir, will you please tell me how much time has been left so that I will also explain about the books which I have included in my PPT. Please stop me before 3 minutes so that I can explain about the books to all of students. Okay. What will be the form of the solution of this PD? U equals to uxy. Transform this right hand side to left hand side. So it can be written as u minus ux comma y equals to 0. Suppose this is f x comma y. Okay. If y is function of x, then what it represents? It represents a curve. It represents a curve in 2 dimensions. And if u is function of two independent variable, then what does it represent? What does it represent?
Ma'am, we have very less
Anji?
time. Our next speaker is waiting for the
Okay,
lecture.
thank you.
Uh,
Yeah, that's why I asked you. Just give me 2 minutes. Just give me 2 minutes.
yes, ma'am.
Oh,
Yes.
sorry.
Is there any question from the participants?
Uh,
मैंने
वो बंद कर दी, वो भी होस्ट थी ना।
हाँ आले की तुझे फ्रेंड्स थी
तुम सही बटन दबाओ।
Okay, I think there was something issue from the host, so I just lost the network. Okay,
Yes.
what I was telling, just click on these two links and then you will get the book. Is my screen is visible to all of you?
No, ma'am.
Okay. Okay, so this PPT I will share. When you will click on these two links, you will get the books. Just download the book from my Google Drive link. You don't need to go through the Google. Just you will click here and then you will get the book. And this is the very basic book by K. Sankarara, an Indian author, and it is very well written. So just try to read this book, the first two chapter of this book, which I have explained. Okay. So thanks to all of you and best of luck for all the other lectures.
Thank you so much, ma'am, for giving such an valuable information about partial differential equations. It will definitely help us.
Yeah, thank you.
Thank you so much, ma'am. Now I would like to invite our next speaker, Dr. Vineet Kumar Singh sir from IIT BHU India. He is Associate Professor of Department of Mathematical Sciences at IIT BHU India. He obtained his PhD in wavelets-based techniques to compute Hankel transform and operational matrix methods for Abel's inversion and certain variational problems. Also, he was postdoctoral fellow at Kursk State University, Russia. His area of interests are computational method for integral equations and differential equations, wavelets analysis, operational matrix methods, and signal processing. Welcome, sir. You may please share your valuable experience and knowledge with us.
Yeah, thank you. Thank you, Dr. Rahul. Are you getting my sound?
Yes, sir.
Hello, Dr. Rahul. Okay, are you getting my sound?
Yes, sir. Yes.
Okay. So thank you, Dr. Rahul, regarding the brief introduction and this invitation in the concern given workshop. And I congratulate you that I have seen that many the PhD student have joined, as well as faculty members are also have joined to regarding this workshop. So I decided this is a workshop, so that's why I have chosen the very basic topic of the research, that is the stability analysis of numerical schemes for ordinary differential equation. So those who are working in the area of numerical scheme or computational scheme for integral equation or ordinary differential equation or partial differential equation, that is one of the major concerns, that to discuss the stability analysis of the designed scheme. And there are also other major concerns, like to discuss about the convergence analysis and as well as order of convergence of the proposed scheme. So, but in this talk, I will only focus on that what is the stability analysis, and what is the how to do the stability analysis for the proposed scheme. So basically, this talk I have divided in three steps. In the first step, I will discuss about the definition of stability analysis, and then I will come to one example, and through example, I have taken simple example of ordinary differential equation with initial condition. So means initial value problem I have chosen for to analyze the stability analysis. So through example, I will verify some the properties. What is the exactly meaning of the stability analysis of the ordinary differential equation, and then in the same step, I have taken the way how we can analyze the stability analysis of the any given model. So I have given some model also, and then for that model we can discuss about the stability. And then I come to the second step. In the second step of the talk, I will come to the that how to define the stability analysis for the proposed scheme. Okay, so for that purpose, I have chosen the same model, and then I have applied the well-known scheme, numerical scheme, that is Euler method and modified Euler method. And then we will see that the proposed scheme or proposed designed scheme is stable, and sometimes it is not stable also. It is conditionally stable. So whenever you're talking about the numerical scheme, we are talking about two types of stability. The one stability is theoretical stability, okay, and second stability is numerical stability.
Sir,
So basically in this talk,
visible
hello,
to us. Sir, your screen is not visible to us. Actually, you are not share your presentation.
yeah, I'll just say I just given the introduction, so I not started the lecture still.
Okay, sir. Sorry, I
So
confused.
now are you getting now? Yeah. Are you getting the title?
Yeah, yes.
Yeah. So just I have given the overview of the title, and the title is stability analysis of numerical scheme. Okay. So the in the second step, I will discuss how there are two types of stability. I have told you that one is the theoretical stability for the proposed scheme, and second is the numerical stability. So my here talk is my focus is here only for the theoretical stability analysis. How to do the theoretical stability analysis for a proposed scheme. Okay, whenever you are designing any numerical scheme, we should discuss first the theoretical stability analysis. Okay, this is a really a challenging task, and nowadays if you are communicating any paper, or if you are developing any work, thesis work based on the numerical scheme, and if you wish to publish a good paper in good journal, then that is very means burning topic, means this is a very important topic, the stability analysis of the proposed scheme. If you are submitting any work in any journal without this stability analysis, that journal will not accept that journal will at initial stage they will say that no, that work is not suitable. That is first assumption, that is first means response you will get from this journal. So even I also started the work in the concern area not very long back, but just I started in 2017. Oh yeah, Dr. Rahul is my PhD student. He when he joined our group, research group, he started in the concerned area. He proposed that how to do the stability analysis of the numerical scheme. Before that, I have done numerical stability analysis. During my PhD time, I have done the numerical stability analysis of the proposed scheme. Okay, so I will come to the now talk the outline of the talk. That is the outline of the talk that I told you that the talk will be divided into three steps. In the first step, I discuss definition. Second step, that stability of initial value problem and stability concept of Euler method and with examples. And then some comparison table I have given. Okay. So look, what is the definition say? What is the definition of the stability analysis say? Say that if I have initial value problem, look here I have mentioned very basic initial value problem, y double prime t is equal to f of t by t. Initial condition is given. So how, whenever you're talking about the stability, so with respect to what condition we're going to find the stability analysis, we are going to do some minor perturbation in the initial condition. Okay, so if you do the minor perturbation, minor changes in the initial condition, then we'll see what is the behavior of the solution. Okay, if the behavior will not deviate more after changing, after do the minor modification in the initial condition, if the behavior of the solution will not change more, if the behavior will be still fixed, then in that case we say that your model is stable, okay, with respect to the given perturbation. So how do we analyze this? So we should take this norm, we should find the difference between the closed form solution. Suppose it has the closed form solution y, then we are taking that after the perturbation, the y epsilon is the known solution with respect to the perturbation. Okay, and we are going to take the assumptions that solvability theory will work in both cases. Means without taking the perturbation, the initial value problem must have a unique solution. Existence uniqueness condition must be hold, And similar condition must be hold for y epsilon also. Means for the Potter problem also, we are taking the condition, we are taking the assumptions that it has a unique solution. So it has a unique solution y epsilon. Now we finding what is the difference between these two. If the difference, look here, this is a Potter problem y epsilon and this is a y is the exact solution. The difference is less than some epsilon, c epsilon, and epsilon is very small. And if epsilon is very small, and that implies the error between these two solution, the closed form solution and Potter solution is less than epsilon, then in that case we say that your solution, whatever the solution we have, that is stable. Means solutions should not deviate more. Okay, whenever you do the perturbation, solutions should not deviate more with respect to the original solution. Okay, so I have taken one simple example. I have taken this y double prime t equal to minus yt plus 1 with initial condition of y0 is 1, and it has a solution yt is 1. Okay, under that assumptions. But I have done the simple modification. I have perturbed the initial condition with respect with epsilon value. Means in the initial condition, I have added one epsilon term, that is a perturbation, and then I have found the solution. The closed form solution we received is 1 plus epsilon or minus t. Okay, and then we have seen that the difference between these two solutions, the exact solution and perturbation solution, have the upper bound which depending on the epsilon. So when epsilon is, we have seen that when epsilon is very small, the difference between these two solutions is not very high and not very large. That means we can say physically, that means that solution not deviate more. That means that problem is said to be stable. Okay, that is the meaning of the stability, okay, of the proposed model. So these are the concern that when minimum error is not much larger than epsilon, then we say initial value problem is well conditioned, and when it is larger, we say ill conditioned. Okay, these are very basic. And there is one theorem that is known as first derivative test for stability. You see that suggests that if you have the equation, so what is the equilibrium point? X naught is known as equilibrium point if f of x naught is 0. Okay, so whenever you're talking about the stability, we are talking about the equilibrium point also. So if x prime equal to fx is some differential autonomous differential equation is given, then x naught would be the equilibrium point if f of x naught will be 0. We're looking for all those x naught for which the f of x is 0. So if f prime x naught is less than 0, then x naught is an asymptotic stable equilibrium. If f prime x naught is greater than 0, then x naught is an unstable equilibrium. And if f prime x naught is 0, then it is that then we say the test is fails. We cannot predict any information through this theorem. Okay, so why I'm discussing this theorem here and all this content, because whenever you wish to work on that concern area on concern topic, you should know about the basic. I have seen many research scholar in our department as well as in other department also. They have published many work in the concerned area, but whenever you ask what is the stability exactly, they could not reply the answer. So you should know about the first basic, and then we can do the good work in the concerned area. Okay, whenever you're talking about the numerical scheme, the stability is one of the major concerns, I told you. So now look here, I have given one simple equation, dx by dt equal to x1 minus x. So we are talking about the phase analysis. So whenever you do the phase analysis, so phase analysis is the one of the pattern, one of the analysis which stability property of the given model. So I have just taken look here, the x1 minus x, behavior of x1 minus x, right hand side part. So when x is lie between 0 to 1, we're looking the behavior of this. So dx by dt will be greater than 0. Means this is dx by dt is tangent line. We can say this is tangent line. So tangent line is positive. Means tangent line to the solution is positive. Dx by dt is what? Is the tangent line to the solution. Whatever the solution will get from the equation 5, we're getting the tangent line, and that tangent line is positive. That implies solution is increasing. If x is less than 0, then dx by dt is less than 0. That means tangent line is negative. Means solution is decreasing. So we can predict the nature of the solution by using this concept, the phase analysis, that solution is increasing or decreasing. And based on this, we can predict the solution is stable or not nearby equilibrium point. So I have just to come to the next example. Look this example. Through this example, we can analyze that why this differential equation is stable. Look, this is dx by dt is equal to 3 minus x with some initial conditions. Now question is here, look here, x equal to 3 is critical point. That is equilibrium point we say, because 3 minus x will be 0 when x is 3. That's why x equal to 3 is critical point. Now we need to judge the behavior of the tangent line to the solution. What would be the nature of we are looking for, what would be the nature of the solution, and what would be the nature of the tangent line to the solution. So when x is greater than 3, then dx by dt is negative. So when the tangent line is negative, means slope is negative, means function is decreasing, means solution is decreasing. When x is less than 3, that means the dx by dt is positive, means tangent line is positive, that means slope is positive. When slope is positive, then function is increasing, means solution is increasing. So with the help of this data, with the help of this analysis, we can judge that solution nearby critical, the behavior of a solution nearby equilibrium point. Nearby equilibrium point, we can judge the solution is stable or unstable or semi-stable. Okay. So look here, I have given this graphical representation. The x equal to 3 is equilibrium solution. So we have seen that the solution is, if you x is greater than 3, we see that solution is increasing, and if x is less than 3, then solution is decreasing. Sorry, when x is greater than 3, solution is decreasing. When x is less than 3, solution is increasing. So we have seen that solution will come near to the equilibrium point, means we can say that solution is stable. So look here, this C is known as a stable point. This is equilibrium point. Sorry, this C is a equilibrium point. So when the tangent line, we have seen when tangent line is going to be negative, then we have seen that the solution behavior of solution will be decreasing, that will tending to the point C. And when the x is less than C, we have seen the solution is positive, means increasing, means hitting the equilibrium point. So in that case, we getting the stable solution. When solution will come nearby the equilibrium point, the behavior will come nearby the equilibrium point. In an unstable case, when the tangent line is the positive, when x is greater than C, when tangent line is positive, solution is increasing. So it's far away from the C. And when x is greater less than C, means the tangent line is negative, means solution is decreasing. It's go beyond the C again, means we have seen the nature of the solution is unstable. It's far away from the equilibrium point. And likewise, we can define semi-stable with respect to the one side, and again with respect to the other side. Okay, so these are the theoretical analysis. These are the theoretical concept for the stability of the ordinary differential equation. We can do for not for all initial value problem, we can do in same way. There is some other procedure also, but for the simplest case, for anomalous problem, we can do this procedure to check the stability of the proposed model, okay, by using this procedure. So these are the equilibrium point. So if it is stable, if the solution stay nearby this equilibrium point, and if it is far away from the equilibrium point, then solution is known as unstable. So what is the theoretical points we have now received? A numerical initial value problem solver is zero stable if small perturbation in the initial condition do not cause numerical approximation to diverge away from the true solution. Okay, then provided that true solution of initial value problem is bounded, that is the condition should be given. And stable numerical method is one for which the numerical solution is well behaved when considering small perturbation, and provided the step size is sufficiently small. In actual computation, that step size, we are not taking any value of any small value, where there should be some condition. We cannot choose any step size. Okay, so I'm coming to this part now. So I told you that this is a second step of my talk, that stability analysis of the differential equation. So in this slide, I have just taken the one simple first order differential equation with equation number 7, which is initial value problem, and I have actually to find the solution of problem 7 is really sometimes is very complicated. So that's why we have taken here simpler form of the equation number 7, which is written in form of equation number 8. So equation number 8 is the special case of equation number 7, when f of t yt has been written in form of lambda yt plus gt. So for the equation number 8, we are going to take the assumption, suppose this problem has a unique solution. Existence uniqueness condition is hold. We're going to take these assumptions. And suppose this problem has a exact solution. Okay. So then question is, how do we analyze the stability of this proposed model 8? This is question. The question is here that how do we analyze this proposed model 8 is stable? So we're going to do this practice, we're going to do this job here, and we'll see that the solution, first I'll find the perturbation in the initial condition, I'll put some perturbation in the initial condition, and then I'll find the error solution. I'll find the error solution. The error solution means I will find the error solution between what? Between the mathematical model 8 and the modified mathematical model 9. 9 means this one. Okay. So I have received the equation number 9 by taking some minor modification in the initial condition, and z epsilon t is the what? Z epsilon t is the changes in the solution, the error solution. Okay, this error solution is with respect to given epsilon. Then I received simply the differential equation in terms of error solution. This is error solution z epsilon t, and we received that solution is lambda z epsilon t, and the initial condition is also given in equation number 11. So you know that the equation number 11 is very well known first order differential equation that can be solved very easily, and we have the solution. The error solution will be epsilon e to the power lambda t. Now the question is, how do we analyze the stability of this solution? Okay, and what is the meaning of stability of the solution here? The stability of the solution here is, we're looking the nature of z epsilon t when t is very large. We are looking what would be the behavior of epsilon, how much epsilon will impact on the given solution z epsilon t when t is very large. So but lambda should be, we are taking here negative real number, lambda should be less than 0 or any. Okay, if lambda is less than 0, then it has some physical meaning. That's why we are considering here lambda less than 0. So if you look here, when lambda is look here, I have mentioned the condition on the lambda. For physical region, I have mentioned lambda should be either a real negative, or lambda should be complex with negative real part. These are the condition on the lambda. So in the such case, we can see that z epsilon t will goes to what? We go to the 0 as t tends to infinity. Means this the outcome solution with respect to the perturb solution, we getting that which tends to 0 as t tends to infinity. Okay, so that means what? That solution we have here, it doesn't depends on this perturbation for large t. So same behavior, that means that say that the behavior of epsilon is not impacting more, okay, on the solution behavior. So that means your solution is what? That solution is stable. Means if in the error solution, we getting the error solution in terms of epsilon, but error solution is not impacting more for large t. That means solution behavior will not impact more. So means whatever the perturbation we have, that will not impact more, okay, for large t. Means thus the perturbed solution is not deviating more from the original solution. So deviation is very small, deviation is not too high with respect to the original solution. So in that case, we say that your solution is stable. That is the meaning of the stability, the stable solution of the proposed model. Now the next question will come. We would like to the same behavior to hold for numerical method that being applied to it. Now I am talking about the next step. Now, what is the meaning of the stability analysis of the proposed numerical scheme? How do we analyze the stability analysis of the proposed numerical scheme? So I have taken the same model. Means I have taken the same model means what? I have taken the same model 8, and I wish to apply here some well-known numerical scheme on equation number 8, and then we'll see that after applying the numerical scheme, I will get some solution. So with the help of the solution, how do you analyze that your solution is stable? So what should we do? So first, we have seen that the solution behavior through this closed form, that solution behavior, what is the solution behavior? Solution behavior is what? Z epsilon t should tends to 0. So same behavior we're looking for the numerical solution also when t is very large. Means what we are looking here? Look here. We're looking that this this behavior, Z epsilon t behavior, we should get for the numerical scheme also. Means whenever you're finding the numerical solution, suppose we receive the numerical solution is yst, which I have mentioned in the next slide. Yst, look here, this one. The question is, the kind of stability property you would like for the numerical method is that when it is applied to 12, the numerical solution must satisfy this behavior. Whenever you are applying the any numerical scheme to the problem, given problem 9, given problem 12, we should get the behavior. This behavior means y of stn should be tends to 0, stn tends to infinity under the choice of what? Under the any choice of step size h. We should not have any restriction on the h. So look, whenever you're finding the any numerical solution, so we are finding numerical solution with respect to some discretization. So suppose we have done some discretization with respect to step size h. So whenever you're finding the solution, that solution is depending on the, if the solution behavior are depending on the step size, then we say that solution is conditionally stable. If the solution behavior not depending on the step size, is free from step size, we say that the solution is what? Your proposed numerical solution is what? Unconditionally stable. So in the theoretical stability analysis, there are two types of step we need to discuss. The first step is conditionally stable and unconditionally stable. So whenever you're talking about the any proposed, any design numerical scheme, we should discuss always that is that method is conditionally stable or unconditional. So conditionally stable means there should be some condition for given as some fixed step size, will get this behavior ystn tends to 0 as tn tends to infinity for fixed step size. But for unconditionally stable, the proposed numerical solution will be goes to 0 for any step size as tn goes to infinity. That is a task. So let's start. I have taken the two well-known numerical scheme for the given mathematical model 12. Okay, so mathematical model 12 is given, and its well-known solution is yt is e to the power lambda t. So you can judge the behavior of now. What is the behavior of the solution? What is the behavior of the equation 13? If you look the behavior of the equation 13, it tending to 0 when lambda is less than 0. Okay, means exact solution behavior will be tending to 0 when the lambda is less than 0. So what do you need with respect to the new numerical solution? So with respect to the proposed numerical solution, I need same behavior for the solution. Whatever the solution you're getting, that solution must goes to 0 when t goes to infinity, under the assumption when lambda is less than 0 for any step. Then the proposed numerical scheme would be stable. And this task we can do for any mathematical model. If the mathematical model is given as in form of integral equation or in terms of ordinary differential equation or even for PD, first we should find out the numerical solution, and then we should take out that what is the behavior of the solution, okay, when t is very large, or error solution. We should come to the error solution also. When to look here, I have decided I have taken here two types of numerical method. I have chosen two numerical method, well-known numerical method. One is Euler method. All of you know that for initial value problem, there are a lot of numerical scheme are available. Well-known numerical scheme are available. The one of the numerical scheme is Euler method, and second scheme is modified Euler method and Runge-Kutta method also available. But I have chosen only two methods. I have taken the same model, equation number 12, and I have designed the Euler method for the given model 12. Then I received that the solution in form of, through this I received the solution in form of what? Yn. Look here, Yn is given in the form of that solution, and Yn is what? 1 plus lambda s to the power n. You know how to implement the Euler method for initial value problem. So the Euler method is Yn plus 1 equal to Yn plus s lambda Yn. So I received finally Yn plus 1 is 1 plus s lambda Yn. When n is greater than 0, y0 is 1. So by induction, it is not difficult to find what is exactly Yn. Okay, when n is 0, I can find y1. When n is 2, I can find y2 in terms of y0. When in terms of y1, and then when n is 3 and 4, I can find all the y3, y4, y5 in terms of this form. So finally, by induction, I received Yn, the numerical solution I received Yn through Euler method for given proposed model 12 is 1 plus lambda s to the power n. Now, tell me what would be the value of Yn if n tending to n means that is nothing but that is node points. Okay, so number of node points is given here. So if suppose n is tending to infinity, what would be the nature of Yn? So you can see that nature must be what? The nature must be what the nature we are predicting. We are predicting the nature that Yn should be tending to 0 when node point is very high. So we are predicting that what we are expecting from the numerical solution, we are expecting that the proposed numerical solution should behave like the closed form solution. So what is the closed form solution? The closed form solution, we know that is in terms of E lambda t, and that tending to 0 when lambda is less than 0. Same behavior we are expecting from equation number 16. So now we'll see that when n is very large, we have seen that will converge to the Yn will tend to the E lambda t bar, and that will tend to the 0 under some assumptions. Now what we getting the assumptions? We getting the assumptions that this 16, that outcome of the solution, the 16, equation number 16 is tending to 0 as n tending to infinity if and only if this condition hold, 1 plus s lambda less than 1. Means equation number 18 must be hold to verify this Yn tending to 0. Okay, means it has the same behavior as the original solution, that as the closed form solution, but under assumption. What is the assumption? That assumption is given the value of h should satisfying this condition. Means value of h lambda should satisfying the condition between -2 to 0, or we can say s should lie between 0 to 2 by lambda. So if you take any value of method will not have the which property? The stability property. We have to choose the value of step size h according to given condition. Then we can see the solution behavior of numerical solution behavior of the proposed model is equivalent to the closed form solution. Means Yn will be tending to 0 only and only if this step size you have chosen. If you have not chosen this step size, the solution will be not stable. Means solution is stable what? Under some condition. So that's why the Euler method, the proposed Euler method for initial value problem is what? Is conditionally stable. Okay, that is the reason that the Euler method, sometime if you proposing any numerical scheme by using forward scheme, by using forward operator, the sometime you getting that that the scheme is not stable. It is unstable. Unstable means conditionally stable. Sorry, I should say conditionally stable. But suppose you need the unconditionally stable scheme, then what should I do? So I have taken some example to verify this. I have taken this example when lambda is -100. So in this case, h value should be less than 0.02. If h is less than 0.02, then that scheme will provide you that solution. So this is conditionally stable. means that behavior of this numerical solution will be equivalent to the corresponding solution under the assumptions that H must satisfy the given condition 0.02 per given lambda. But suppose I need a solution which satisfies the numerical solution behavior equivalent to the corresponding solution for any H. So could we get that through the Euler method? The Euler method, the forward Euler method scheme? So no. So for that purpose, we have tested for modified Euler method, that is, we say backward Euler method. So what is the backward Euler method? So backward Euler method means we have replaced y prime t by 1 by h yt minus h. That is the backward operator. All of you are familiar with this. So I should not discuss. I should not focus on more on that. So you know how to replace the derivative by the backward difference. When you replace by the forward, by this is a forward, we receive the numerical scheme which is conditionally stable. Now we're going to check the behavior of the model 12, which I proposed, and we have seen again the solution, numerical solution behavior by using equation number 21. I have seen by using 20. By using 20, I replace y prime by the 20, and then we have seen that the numerical solution is conditionally stable. Now we're going to check what would be the behavior of the numerical solution when you use the equation number 21. Whenever you're going to try for this, so we are getting what? We are getting the Euler, we getting the backward Euler method for the proposed model for the same model is like this. Okay, yn will be yn minus n plus s time f of t n yn. You know how to apply the initial value problem any Euler method. Same procedure we have to do here, and then through this we can get finally this outcome. So we have received our outcome yn plus 1 is 1 minus h lambda power minus 1 yn for n greater than equal to 0. Now with initial condition is given y naught is 1, and by using induction, take n is 1, then we can write y1 in terms of y naught. Take n is 2, then I can write y2 in terms of y1 and y1 in terms of y naught. And take n is 3, then similarly take n is n plus 1. So finally we can get the yn, which will be free from the right hand side. Look, in the right hand side we have yn. So I wish to find the yn which must be free from the yn component. Okay, in the right hand side we getting yn, and left hand side we getting yn plus 1. So I wish to find yn which must be free from y. The right hand side must be free from y. For that purpose I have used the induction, and then I received yn in terms of 1 minus s lambda power minus n. So that is the solution. Now 24, equation 24 is what? The solution of the given model, the same model which I have done by using Euler method. I have done by the Euler method, I received this solution. If you remember, I received this solution. I will come to the previous slide. I received this solution. Equation number 16 is the solution when I have used Euler method, plain Euler method, means forward operator I have used. But when I have used backward Euler method, I have received yn is what? I have received yn is this one. So look, what would change now? What we going to see the modification after implementing the modified Euler method, I will say backward Euler method. So we have seen that for any step size s greater than 0, yn tending to 0, because 1 minus s lambda is greater than 1 always. Why it is greater than 1 always? Because lambda is negative. If you look, 1 minus s lambda, that will tends to 0. Okay, when n tends to infinity for any step size. There is no restriction on step size. Okay, in 24, the 24 outcome, that is the outcome of the given model, that is the solution of the given model by using backward Euler method, which is free from step size. The behavior of the solution is free from step size, because yn will tends to 0 when n tends to infinity for any step size. The reason is because lambda is negative, so 1 minus h lambda, and h is is a given value, so 1 minus s lambda will be always what? Greater than 1, because lambda is negative. So 1 minus s lambda will be always greater than 1. So that's why is yn tending to 0 as n tends to infinity. Okay. So if we have come to this table, that table is calculated based on the given node points. I have taken h is 0.1, h is 0.05, and h is 0.01. So we have seen that when step size is very low, we getting very accurate solution. And that solution, if you compare this solution with the previous data by using Euler method for the proposed model, if you compare with this data, look this, when h is 0.1 is received, yn at 0.2 is 81, and when 0.05 is 256. So look how much it's variate now, deviate the solution. The solution deviation is too high, but when h is 0.01, we getting the error is 10 to the power minus 10. Okay. So when step size is come under the condition 0.02, you know the step size, what should be the step size? So when step size is near to 0.02, less than 0.02, then you will get the better error, because this is conditionally stable. But this scheme, but modified Euler method is what? The modified Euler method is say that to take any step size, but solution will be better. But if you take the step size very less, then definitely it will be best solution. Okay. But it is the solution behavior definitely the for large n, if you going for large n, the solution behavior will be similar to the a closed form solution. Okay. So what we have received through this, we have received that I have taken the final conclusion is that I have taken the one simple model. I have taken the simple model means this model which I have proposed here. Come to equation number 12. Okay. So the final conclusion is, if you want to do the stability analysis for the any new design scheme, okay, then we have to do like this. We have to first find the what is the nature of the solution, what is the mathematical model is given. So mathematical model is initial value problem is given. You design the scheme. So I designed two schemes. The first is Euler method. Second is modified backward Euler method. We have seen that the solution behavior of the Euler method is having the same behavior as the closed form solution e to the power lambda t, but under some condition. That's why that is known as conditionally stable. In the second scheme, we have received the solution behavior which is exact, which have the same behavior as equation number 13, but under the condition is that we have taken any step size. For any step size, the Euler method, the backward Euler method, have the solution behavior exactly equal to equation number 13 for large t. Okay. So means this is a conclusion that whenever you're going to develop any numerical scheme, you should try like this. You should use whenever you're going to do the discretization, whenever you're going to do the any by any numerical scheme, you should first analyze what is the nature of the solution. If you know the nature of the solution, we can predict exactly how we can find the scheme is stable or non-stable, okay, or conditionally stable. So now I'm coming to the other part of the talk, that is here stability of nonlinear ODE. So I have discussed about the only linear ODE. Just I give you the some sketch idea about how to do for the stability analysis of nonlinear ODE. Okay, those who wish to work for the any mathematical model which is non-linear, how to predict, how to find the stability condition, how to find the scheme is stable or conditionally stable. So these are the content are given with respect to this. Sometimes very challenging task to find the solution of nonlinear ODE. Okay, but if you have the solution of the nonlinear ODE, then how do you analyze that solution is stable? The same procedure we have to do like we have done for the linear ODE, same procedure we have to do for nonlinear, but there is some linearization technique is there. We have to linearize the problem and then we can find the behavior of the stability of the given solution. So the two authors are given the work, have proposed the work on that area. Vidyasagar in 1930 93 and 92, the two authors have proposed the scheme that is first method is known as stability analysis by using the function, and second method is based on linearization the system around its equilibrium point. So these are the two techniques to analyze the stability analysis of any nonlinear ODE. If you wish to analyze for the nonlinear ODE, these two methods are well known. So you have to use the energy method or you have to use the linearization technique. Okay, so that are based on the first method. If you want to do by using first method, that is based on the is called a direct method, and second method is called indirect method. So these are the content, and thank you. So any questions? Any
Any
questions?
questions from participants? Participants can unmute their mics and ask questions.
Yeah, because that is really. I have seen as a reviewer also the mini paper, and I could not find this concern means stability analysis. The proposing scheme is very easy. You can propose the new scheme very easily. But to show that scheme is converged, to show that scheme is stable, to show that scheme has some finite order of convergence, and all this job is really a challenging task for those who are working in the area of numerical analysis. So I will suggest you whenever you are developing any numerical scheme, you should try to develop the stability analysis, you should try to develop convergence analysis, and you should try to develop the order of convergence analysis also. Okay, otherwise without that task the whatever you have proposed a new scheme, that will be not useful for the research community, that will be not useful. Yeah, shall I leave, Dr. Rahul?
Uh,
Dr. Rahul, are you getting me?
if any participants have any doubt, then please ask. Otherwise, sir, you may leave. Uh,
There are L stability and zero stability. Okay, so I have received from the messages. I could not get what the meaning of that. uh, Okay, Rahul, if any student are interested, they may call me also if you wish to work, and if they wish to. Even I have proposed some numerical scheme based on by using matrix, operational matrix scheme also. But still, we are looking for the stability analysis for the by using the proposed operational matrix scheme. Okay.
Okay. Thank you so much, sir. Dr. V.K. Singh, sir, is also PhD supervisor of Dr. R.K. Maurya, sir, convener of this
Yes.
workshop.
Yes. Yes. This is my pleasure.
Yes, sir. Thank
Actually,
you.
Dr. Rahul actually leave our research group within short time, within 3 years, and within this 3 years period, he have published very good paper. But this is unfortunate for our lab, but this is fortunate for the college where he is working. That is really he's good and he's working in the numerical scheme. I hope that in the coming years he will do more job and more work. He more focus on the research. Okay, Rahul, wish you good luck, best wishes,
thank you.
stay
Thank you so
blessed.
much, sir, for this enlightening information about stability analysis of numerical schemes for ordinary differential equations. Thank you so much, sir.
Thank you. Thank you.
Now I would like to invite next speaker of this workshop, Professor Hyginio Ramos from University of Salamanca, Spain. He is professor of Department of Mathematics at University of Salamanca, Spain. Professor Hyginio Ramos has received his PhD in the year 2004 in mathematics from the University of Salamanca. He has more than 105 publications in reputed journals and in particular 74 publications in Scopus with a total of 82 citations thus far. Besides the publications, he has managed around 14 projects and has made 69 presentations of communications. In the year 2004, Professor Hyginio Sir has received extraordinary award for PhD studies for his thesis titled as New Families of Numerical Methods for the Solution of Second Order Initial Value Problems of Oscillatory Type. As a researcher, his key interest areas include numerical analysis and differential equations. Most welcome, sir. Please, you may share your valuable knowledge with us.
Okay, good morning. Thank you for this nice presentation. I'm going to share my screen. Can you see it?
No, sir.
No? No?
Yes, sir.
Okay,
Yes, sir.
thank you. Okay, thank you for inviting me to give this talk. I'm going to talk about the use of block methods for solving partial differential equations. And previous to that, I'm going to talk about block methods. It seems that block methods were firstly proposed by Milne. You can see at the end of the page the title, Numerical Solution of Differential Equations, in 1953. And since then, many people have used this kind of methods for solving different kinds of differential problems. So it can be used for solving initial value problems, boundary value problems, PDEs, fractional differential equations, and so on. Okay, roughly speaking, we can say that a k-step block method is a set of k multi-step formulas that produces k approximate values of the differential problem at k grid points at the same time. So we take a few grid points and we approximate the solution we are looking for at those points at the same time. So this is why it is called a block method. For example, for solving a first order problem, I assume that it is an initial value problem. So we have a differential equation and also an initial value. For example, these two formulas is a method that was proposed by Dinsdale and Klippinger in 1958. And you see that it consists on two formulas, so two linear multi-step formulas, where the approximate solutions of xm plus 1, xm plus 2 are given at the same time after solving this system. So this is a system of equation that produces the two approximate solutions. Okay, this is just one example, but there are many other two-step block methods in the literature. For example, these are other two formulations of two-step block methods. But in fact, all these two-step block methods are different formulations of the same block method. So let's see how we can develop any two-step block method. For this, we are going to consider an interval with 3 points. So we have xn, xn plus 1, xn plus 2. And for these values, we want to get approximate values of the solution, which are these. Okay, we assume that the first point, we had the initial value. So yn is known and fn is also known. So in fact, here we also have two unknowns, because fn plus 1, fn plus 2 can be put in terms of the other values. So the unknowns are yn plus 1, yn plus 2. So we have two unknowns here. So we have other four, say, information, or these values and those ones, which we are going to use to formulate the method. So as we have four unknown, four values here at our disposal, we consider a polynomial. We can use polynomial approximations, or we can use other approximations using trigonometric functions, exponential functions, or other kind of approximations. But the usual one is to use polynomial approximation. So in this case, we consider this polynomial, which goes from 0 to 3, the powers. So we have a polynomial of order 3, where we have four unknowns. As we have four pieces of information here, we are going to use these pieces of information to obtain the coefficients of the polynomial. So we impose the interpolation and collocation conditions to obtain the four coefficients. So we have these four equations using the pieces of information we have, and we solve this system to get the coefficients. And after that, putting the coefficients, we approximate the polynomial of xn plus 1, xn plus 2, and we obtain the two solutions, the two approximate solutions of our problem. So this is a two-step block method. So to solve the problem, we have to solve this system. The usual way to solve the system is to use the Newton's method. Using this Newton's method and solving the system, we obtain two approximate solutions for our problem. So we obtain the two solutions at the same time. And then we continue this procedure and obtain the next solution for the next two-step block, and so on, until we reach the final point in the interval we want to solve the problem. The same approach can be used for three-step block method. In this case, we consider xn, xn plus 1, n plus 2, xn plus 3. So we have 4 points, 3 intervals, and we solve at the same time the problem, the initial value problem we have these intervals. And these are the formulas you can obtain similarly as I showed you before for the two-step block method. And solving this system, you get approximate values at the same time at 3 points. There are different formulations for this three-step block method. The simplest one is this one at the end of the slide, where instead of expressing the values of yn plus 1, yn plus 2, yn plus 3, we have fn plus 1, fn plus 2, fn plus 3. So what is the difference between these two formulations? The difference is that f appears many times on the right-hand side of this method, of this formulation. And in this case, f does not appear in the right-hand side of these formulas. Well, there is fn, but fn is a value, is a number, because you know f, you know xn, which is the first point, the initial value. You know way n, so you can evaluate this function. This is just a number. So the only appearances of f in terms of the function you have on the right-hand side of the differential equation is on the left of these formulas. So just one time for each evaluation of the f. This means that if f is a complicated function, this is a more simple form of the system to be solved. And this results in a saving in computational time. Well, now let's see how to formulate a two-step IRE method. So in this case, IRE means that you use intermediate points. So we have the grid points xn, xn plus 1, xn plus 2, and we consider two intermediate points. So in this case, we have that the unknowns are 4, so these are the unknowns, but we have more tens that we can use to formulate the method. So we have exactly 1, 2, 3, 4, 5, 6 tens to formulate the approximation by a polynomial, as we did previously. So the difference now is that we have considered two intermediate points. So we have x n plus r x, which is an intermediate point, or xr. I call here, yes, xr, but it's similar to use this notation is the same. So we have two intermediate points where we look for those values of the parameters r and s, which must be between 0 and 1 and 1 and 2 respectively. So if we take this polynomial approximation, we solve the system as before to obtain the coefficients. Those coefficients will be expressed in terms of the values at our disposal, that is, those values, all those values. So this is the system to get the coefficient of the polynomial, and then we apply the polynomial to the points xn plus 1 and xn plus 2, we obtain two formulas for approximating the exact values at those points. So the question now is how to get the parameters r and s, which correspond to the intermediate points. So this can be done using the local truncation errors of these two formulas, because these local truncation errors, which are obtained using the usual Taylor expansion. So we expand the formula to approximate way at xn plus 1 using the Taylor expansion, we get this local truncation error. So this local truncation error is expressed in terms of the parameters r and s, which are related, which correspond to the intermediate points. So if we take this term, the principal term of the local truncation error for the approximation of xn plus 1, and also this term, the principal term of the local truncation error of yn plus 2, and impose that this term vanish, we get a system, an algebraic system of two equations. After solving this system, we obtain the values for those parameters. So these are the optimized values for this block method. Optimize in this case means that the approximations for the two main terms, that is the approximate values at the grid points, the errors have a higher order, because if we take those values, the principal terms in the local truncation errors vanish. So in fact, we have a power of 7 for the approximation, those approximations in the local truncation error. So taking those values we have obtained, we can formulate the 4 formulas of the hybrid block method. So this is one of them, this is the other one, and the last two are this and this. So we have 4 formulas, we have 4 unknowns. So solving this system, we obtain the 4 unknowns we want. So the 4 approximations at the 2 grid points, but also at the intermediate points. Well, as I told you before, the block methods may be used for solving different kinds of differential equations. In particular, they can be used for solving second-order differential equations, and in particular, for solving boundary value problems. So in this case, what is the difference? The difference is that we cannot use the block method sequentially. So we don't have initial values, in this case, for the solution and the derivative, in order to apply to the, say, two-step block method at the 2 first intervals and the 2 second intervals, and so on. Because we have, for example, if we consider the Dirichlet boundary conditions, we have information at the first point and information at the last one. So AB is the integration interval. Also, we can have, for example, values of the derivatives. So in this case, we have Newman boundary conditions or mixed boundary conditions, having just an equation related with the first point and with the last one. So the 2n intervals. So let's see how to apply the method. Firstly, I'm going to show you how to obtain a method for solving second-order differential equation where you use third derivatives. So in this case, as we want a two-step block method, we consider also 3 points. We have these values where the unknowns, may be, in this case, all of them. And the unknowns for the solution, for the derivative, and these are values that are expressed in terms of the previous values. And in this case, G corresponds to the third derivative. The third derivative means the first derivative of f. So you can obtain this expression of the first derivative of the function f. So you can express this in terms of the unknowns. So in this case, we are going to consider all these pieces of information. So in this case, we have 1, 2, 3, 4, 5, 6, 7, 8 pieces of information. So in this case, we consider a polynomial approximation of degree 7. So the procedure is similar as before. We have 8 unknowns, 8 coefficients, known coefficients. We impose conditions on the polynomial at the different points, the polynomial, the derivative, the second derivative. We obtain the coefficients expressed in terms of those values. Polynomial, we can apply the polynomial and the first derivative at the point xn plus 2, we obtain those formulas. So in this case, we have 2 formulas, one to approximate the solution of the problem, one to approximate the first derivative of the problem. So you see that in this case, in these formulas, there appears values of the derivatives, there appear values of the function, there appears values of the third derivative of the solution, the first derivative of f. So we have, in this case, these 2 formulas for the approximate, to get the approximate values. But the question is now that we have to solve a boundary value problem. So in this case, we have to formulate a system corresponding to this value problem. This system, in fact, is a discretization of the problem along the grid points. So in this case, we are going to consider for n equals 0, 1, 2, n minus 2, the above formulas. This gives a total of 2 times n minus 1 equations. So we have also 2 boundary conditions. So the total of the formulas we have is 2 times n equations. So it is assumed that we have divided the interval of integration considering this grid point x0, x1, x2, xn plus 2. In this case, taking a uniform step size. There are, in this case, 2 times n plus 1 unknowns that corresponds the values of the solution and the derivative along all the grid points. So we need, in this case, 2 more formulas in order to complete a system of the same number of equations as the number of unknowns. But in this case, we can take those formulas. These formulas are obtained similarly as before, but in this case, using only the first points. So x0, x1, x2. So we formulate these formulas using the pieces of information you see here. So this is to complete a system of 2n plus 2 equations in order to get, at the same time, because now we have a big system of algebraic equations, and solving this system, we obtain at the same time all the unknowns, which are all those values you can see here. So all the approximate values of the solution and all the approximate values of the first derivative. Usually, when you solve second-order problems, you are interested in the approximate values of the first derivative. If you are not interested in those values, sometimes you can reduce the number of equations. And in this case, you also can save computational time. But it depends on the problem you want to solve, and if you are or not interested in the derivatives. Well, let's see a numerical example about the use of this block method. So in this case, we have a system And we have boundary conditions. So we have a system with two second-order differential equations. To be solved on this interval, we have those boundary conditions at the initial value at the final point. These are the right-hand side of the differential equations of F1, F2 are given by this. And the exact solution of the problem in this case is this one. So this is used just to compute the errors that the method produces. So this is a comparison using a method which use radial basis functions and a differential quadrature that have appeared in this paper. So the first lines correspond to the two-step block method. So in this case, you can see that the errors are less with the two-step block method than those obtained with the differential quadrature method in this paper. So this is the step size, the fixed step size used. I take this in order to compare with the step size used in this paper, and you see that the errors are much better with the two-step block method. So this is just a picture of the exact and the numerical solution, where you can see that they agree very, very well. And this is the second solution. Now let's see how to develop a two-step ivory block method, also for solving second-order problems. It can be used for solving initial value problems, as I told you before, or for solving boundary value problems. So the difference between one case and another is how you apply the method. You apply the method sequentially in case of initial value problem, and you apply the method globally. You formulate all the equations at the same time in case of boundary value problems. So in this case, we consider a two-step block method and intermediate values. You see here what are the intermediate values. And we are going also to take here values of the third derivatives. So the first derivative of f, according to the problem we have. So in this case, the unknowns are those, and the pieces of information we have to formulate the method are the rest. So we have 2, 4, 6, 8, 9. So we are going to take a polynomial approximation where the polynomial is of degree 8. So we formulate the system to get the coefficients of the polynomial. And once we have obtained the coefficients of the polynomial, we evaluate the polynomial with these coefficients. At this point, xn plus 2, we obtain the corresponding formula. We obtain also the formula for the first derivative of the polynomial, and we have two formulas. These two formulas are expressed in terms of the parameters, that is, in this case, p and q, which are the name corresponding to the parameters corresponding to the intermediate points. So we take the local truncation error for the formula to approximate the solution at this point. We take the local truncation error for the solution to approximate the first derivative, and at this point also. And these are the errors where we have the local truncation errors in terms of the parameters. So we consider the principal term of these local truncation errors. We vanish those terms, and we get an algebraic system. We solve this algebraic system, and we obtain the values of the two parameters. So we have obtained an optimized block method for solving second-order differential equations. This is the formula for the approximation of the solution. This is the formula for the approximation of the first derivative at this point. Also evaluating the polynomial we have obtained at the other points, we found the rest of the formulas. So these are the three formulas to approximate the solution. These are the three formulas to approximate the first derivative. So in total, we have 8 formulas, and we have 8 unknowns. Now, if we want to use this block method for solving boundary value problems, we have to consider these formulas along the integration interval, the total integration interval. So in this case, we proceed in a different way as before, but it is similar. So we take, in this case, as we have all the formulas, we consider n equal 0, 2, and big N, capital N, minus 2. So we take n from 2 by 2. In this case, we must say that n must be an even number because we are using a two-step block method. So we must divide the total number of subintervals in groups of 2, where we are going to apply the block method. So taking these values, we form a big system, and this big system is just a discretization of the problem. We consider also the boundary conditions, and this form a system. Solving this system, we obtain at the same time all the approximate values. Okay, this is an example of the application of this method. This is a second-order problem. We have these two boundary conditions. The first one on the derivative, the second one use the solution and the derivatives at the finite point. So this is mixed boundary conditions. We have 2 equations that constitutes, together with the other ones, the method to solve the problem. So you can see here in this table the maximum absolute errors taking, well, for this problem I took r equals 1, and this is the solution taken, this is the number of points, and this is the errors, that's all the errors with the new scheme, and these are the errors with the scheme in this paper and also in this one. So you see that the block method produces very, very good approximations. So let's see how to apply the block methods for solving PDEs. We are considering this kind of PDEs where we have the first derivative with respect to time and first and second derivatives with respect to the space variable. So in this case, we have boundary conditions and initial conditions to guarantee the uniqueness of the solution. So in this case, what we have to do is to discretize in the space variable. So we take those values. So just in the space variable, and using this step size, we consider approximation for the spatial derivatives, so spatial derivatives with respect to x, the first and the second derivative, using the usual approximations. So this is our second order approximation for the first and the second derivatives. And using these approximations and the grid points on the space variable, this is similar to the method of lines, where we obtain a system of differential equations. So we discretize the problem, the PDE, considering these points, and we get this system. And this system is dependent on the variable t. So what we are going to use is to take the block methods to solve this system. In this case, this is an ordinary system of differential equations. So we solve this ordinary system of differential equation using the block methods I showed you before. For example, if we take the diffusion equation with this boundary and initial condition in this domain, we can solve this taking, for example, n equal 15. So this is the number of grid points along the space variable. So we solve along these lines the problem using the block method. Well, this is the exact and the approximate solutions we obtain. The order of the errors in this case are 10 to the power minus 7. We can use this approach also for solving this equation. In this case, this is a Burger's equation. This is a PDE where we have, well, this is a nonlinear PDE. We have the u here, also the first derivative and the second derivative. So these are the boundary and the initial conditions. We solve this problem taking, in this case, n equals 39. So this is the number of points we take here. We solve the problem of these lines using the block methods. So in this case, you can see also the exact solution, the discrete solution obtained with the block method. The errors are of order of 10 to the power minus 7. Well, another more complicated equation, in this case, we have the second derivative of u to the power 4 and the first derivative of u to the power 3. So we approximate the values using the approach for the first and the second spatial derivatives. Also, we take n equals 39, and we obtain this solution. So as you can see, the way you use the block method for solving PDEs is after using the method of lines, you discretize the PDEs, you obtain a system of ordinary differential equations, and you apply the block methods for solving these equations. And this can be used also for system of PDEs in 1D or even in higher dimensions. It complicates more, of course, the computations and the time, but it can be used. So the conclusions, the block methods are relatively new, but they have been used by many people for solving different kind of differential problems. And when you take intermediate points, you have to optimize these values, because in this way you obtain better results. And this can be done using the local truncation errors, considering the local truncation errors in order to optimize the formulas. There is an open research that I plan for the future. I used to use these block methods for solving singularly perturbed problems where you know it is necessary to take non-uniform measures. I have used non-uniform measures for solving different kind of problems, but not for singularly better problems. But this is an open work for the future. Okay, finally, this is a list of some articles related with this presentation. This is the first work by Milne, where the block methods appear for the first time. This is a work about how are the k-step block methods, the different formulation of k-step block methods. This is just other articles I use to take the problems to be solved with in order to compare. Okay, that's all. So many thanks for your attention.
Thank you, sir. Sir, I have a question. First, any participants wants to ask any question? Participants can unmute to ask questions. Sir, I have a question.
No, there is no questions.
Sir, I have a question.
Okay.
Sir, could you provide any good source for method of lines?
Yes, for the method of lines, there are good books. I don't remember now the name of the person who write, but you can look in Google for method of lines. There are some good books for this. I don't remember the name. Sorry for this.
Sir, please kindly mail it to the convener of the workshop. We will provide email.
Yes.
Sir, one more question I have. Sir, what are the advantages of block method over finite difference method whose computational cost is less?
Well, the computational cost is less compared to other usual methods, Runge-Kutta methods, multi-step method, linear multi-step methods, because you obtain the solution at the same time at 2 grid points or 3, or it depends on the number of the steps you take. And usually, yes, it is less expensive. There's one thing I must say, that block methods are implicit methods. So if you want to solve simple problems, it is not recommended to use block method. Block method must be used for solving complicated problems, steep problems, or higher problems where you obtain a big system after discretizing, for example, the PDE. So for simple problems, it is not necessary to use block methods. But for other problems, they are very good.
Okay, sir. Thank you, sir. Sir, also in chat box, many participants asking for PPT. Sir, could you provide it?
So what?
Sir, in chat box, many participants are asking for PPT. Sir, PPT of this presentation.
Oh, yes, I can provide. Yes, of course.
Okay.
And I include my email there in order if someone want to ask me something. Yes.
Thank you, sir. Thank you, sir. Thank you so much, sir, for
Sir,
your.
my question for numerical simulation. About which software we are using for numerical simulation graphing?
For the numerical simulation, I use Mathematica. Previously, I used MATLAB, but I found some inconsistencies in MATLAB in solving big problems with related with discretization of PDE. So I decided to use Mathematica. So this is what I use. But I think this is, you can use any other program language you want, say Python
Thank you.
or C or any other.
Sir, my question second, we have also taken certain condition in 2n minus 1 condition. So how much degree of polynomial we are assuming? How much degree of polynomial we are assuming for 2n minus condition?
Oh, it depends. It depends on the problem, but usually if you take a big degree polynomial, you obtain better results.
Okay.
But in this case, it is more complicated to formulate the method. Okay.
Thank you, sir.
So usually they take, usually in the literature, they take 3 or 4 as the degree polynomial. But you can use more degrees, higher degree, but it
Okay.
complicates the method to be obtained.
Yogesh Chandra can ask question. I can see you raised your hand, Yogesh Chandra. You can unmute your mic and ask the question. Okay. Okay. Maybe there's some problem for connection. Thank you so much, sir, for sharing your wonderful knowledge with us. Khaled
Okay, thank you very
is
much.
raised his hand.
Hi, sir.
Oh, hi.
Excuse me, sir. Just I want to ask about solving a fractional order nonlinear system with time delay. Could you please suggest me any idea regarding this?
I have not used the block methods for solving fractional differential equations or differential equations containing delay terms, but there are some people that have used these methods for solving this kind of problems. For example, I think Professor Mahid have used these kind of methods. It can be used, but I have not used for solving this problem.
Okay, sir. Thank you.
Anyone else who wants to ask any question? No. Okay. Thank you so much, sir, for sharing your wonderful knowledge about numerical solution of partial differential equations using block methods with us. Thank you so much, sir.
Okay, thank you very much.
Thank you so much, sir.
I want to say you that Scherzer is the guy that had written some books concerning the method of lines.
Yes, sir.
There are very good books, so you can use these books to learn about the method of lines.
Okay, sir. Thank you, sir.
Okay, thank you very much for the invitation. Bye.
And so all the participants can leave now. We will join tomorrow onwards as per the schedule. Thank you so much to all.
ಅಲ್ಲ ಬೇಡ